Good morning, everybody. This is a recording to replace the recording that we have on, or we had on January 18th, because that recording did not have any audio. So I'm recording this to replace that recording. Okay, so we in that class we continued describing the systems and the system properties, and we said one of the properties that we looked at is whether the system is causal or non-causal. And we said the causal system is the system that has an output that depends on the input at that time or at previous time. So therefore, if I look at y at any time n0, if it depends on the input x of n when n is less than or equal to n0, then we call that system causal. If the system is causal, then that system is not anticipating. It does not have to know the future input in order to produce an output. So if you look at this example, y of n equal to 1/2 x of n plus x of n plus 1, this system is not causal. Why? Because at any time, if I take the output y at 0, is going to depend on x at n plus 1, which is going to be x of 0 plus 1, which is x of 1. So therefore, the output is going to depend on a future input, and that makes the system not causal. Another property of the system is whether the system is stable or unstable, and we look at the bounded input, bounded output stability. And the definition of the bounded input, bounded output stability is that if the input is bounded, we want the output to be bounded. So if the input is bounded, and what that means, if the input has a maximum value that is finite. So if this is my input x of n, it has a maximum value. This maximum value is bx, and this bx is finite. It's less than infinity for all values of n. Then we should have an output that is also bounded, that has a maximum value that is by, that is less than infinity. So if you look at a system that is described in this example, y of n equal to n over 3, the summation of x of n, and since we have a finite summation, we can expand that, and that is going to equal to n over 3 multiplied by x of n minus 1 plus x of n plus 1. If you look at the system properties of this system, we can see that the system has memory, because it not only depends on x of n at that time, depends on a previous x of n and a future x of n, therefore it has memory. The system is not causal, because the output at any time will depend on the input at future time, y of n, there is x of n plus 1. The system is linear, and the system is time variant. And the reason the system is time variant is because we have this n, which represent the time, multiplied by x of n. And we said, one way to easily tell whether the system is time variant or not, if the index of the time in the input is anything other than n, then the system will be time variant. So if I have x of n over 3, then the system is time variant. If I have 3n, time variant, n squared, time variant. Another cause of time variance in the system, if the input is multiplied by n. Again, remember, n represent the time. So if I have y of n equal to n multiplied by x of n, that is a time variant. N plus 1 multiplied by x of n, time variant. N squared multiplied by x of n, it is time variant. Okay. Also, this system is unstable. We can see why it is unstable, because of this n multiplied here. So even if I'm given an input that is finite, when n goes to infinity, the output is going to be infinity. Y at infinity is going to equal to infinity multiplied by x of n, the inputs. So even if the input is finite, because of this n that multiplies the input, is going to cause the output to go to infinity. Okay. Now, out of all the systems that we can have, we're going to focus on linear time invariant systems. So this system is linear, and it is time invariant. If we have a system that is linear and time invariant, we can characterize that system by impulse response. So we see this impulse response, and we're going to see it throughout the course. This applies to systems that are linear and time invariant. We have other representation of the systems that we're going to see: the transfer function, difference equation, frequency response. Once we cover the Z transform, we'll go back and try to relate all these different representations of the system. But all these representations, we can go from one representation to the other. So starting with the impulse response, this is one way to represent the system. The impulse response is the response of the system when we apply an impulse to it. So if I have a system that I'm trying to characterize, I apply an impulse, delta of n. I look at the output of the system. That output of the system is h of n, which is the system impulse response. Whatever the output that comes at the output of the system when I applied an impulse, a unit impulse, is our impulse response. Now if we have a system and we know the impulse response for it, so I applied a delta, I got h of n. How do I generate the output of the system when I apply another input? What if I applied x of n? And the way we generate the output of the system is through the convolution of the input with the impulse response. So if I want to calculate the output when I apply x of n, the output is equal to x of n convolved with h of n. Okay, so let's look how, just a refresh on how the convolution looks like. So if we have an example, we have x of n that is equal to 3 at 0, 1 at 1, and we have a system that has an impulse response 4 and 5, and this arrow here means where the 0 index is. So this arrow, it means the 4 is at 0, and then the 1 after it will be at 1. So this is the 0 index, this is the 1 index, 0, this is going to be 1. So we have the h of n that is 4 and 5, 4 at 0, 5 at 1. How do we calculate the output for this system? We can break the input into different impulses. So we have this impulse that is at 0. If we apply it, we're going to get the h of n at the output. So we're going to get the 4 and the 5, the 4 at 0 and the 5 at 1. If I apply the 1, of course, and that's going to be multiplied by 3, because this is a linear system. If I scale the input, I'm going to scale the output. If I applied a unit impulse at 0, I would have gotten 4 and 5, but because I'm applying a 3, I'm going to get 3 times 4 and 3 times 5. This 3 is coming from the fact that the input is not unity. Okay, if we look at the impulse that is happening at 1, is going to also generate for me the h of n. However, h of n is going to be shifted by 1 because the impulse is applied when n is equal to 1. So I'm going to get this response that we see in blue. This is the response of the system that is a result of applying this 1 here. So this one is the blue, and the green is the result of applying the 3. Now if I look into this, this is nothing other than the convolution summation, which tells me that y of n is equal to x of n convolved with h of n is equal the summation from k equal negative infinity to infinity x of k multiplied by h of n minus k. This convolution, evaluating this convolution, will give me the total output of the system for any input. Now, how do we evaluate this convolution? We can evaluate the convolution analytically, graphically, using a table method, or using the computer programs such as MATLAB. So we're going to look first at the calculation of the convolution using the table method. So let's say we have two signals that I want to convolve together. X of n equal to 2, 3, 4. H of n is equal 1, 2, 1, 1. And I want to see what the result of the convolution is. And the way we do the convolution using the table method, I'm going to take one of the signals. In this case, I'm going to take 2, 3, 4. I'm going to write them in a row. So I have 2, 3, and 4. Then I'm going to take the second signal, which is 1, 2, 1, 1, and I'm going to write it vertically. 1, 2, 1, 1. Then I'm going to multiply that row with the entries from the first column. So I'm going to multiply this row with 1. I'm going to get 2, 3, 4. I'm going to multiply this row by 2. I'm going to get 4, 6, 8. Multiplied by 1, I'm going to get 2, 3, 4. By 1, 2, 3, 4. Then what we do is we add the elements diagonally. So if I add these elements diagonally, I'm going to get a 2. Then I'm going to get 3 plus 4, which is a 7. I'm going to get 4 plus 6 plus 2, which is a 12. 8 plus 3 plus 2, which is 13. 4 plus 3, which is 7, and then 4. So the result of the convolution is going to be a 2, a 7, a 12, a 3, 7, and 4. Now, how do we know when is that output going to happen? This does not give me any information about the time index. And we know that the output is going to start, then to know when the output is going to start, we take nx and we add to it nh. So if the input nx starts at 5 and nh starts at 0, then 5 plus 0 is 5, and therefore my output is going to start at 5. ny is going to be nx plus nh, which is 5 plus 0, which is equal to a 5. Okay. Another method of evaluating this integration, this convolution, is graphically. And to evaluate the convolution graphically, if I want to convolve h with x, I'm going to take one of the signals, and in this case I'm going to take h of k, and I'm going to flip it. I'm going to fold it around the y-axis. So I have a 2, 1, negative 1. If I flipped it around the y-axis, I'm going to have 2, 1, negative 1. And then at n equal to 0, I'm going to have a 1 and 0. So you can see this signal is folded. I took this signal, I folded it around the y-axis. What do we do next? We multiply it with x of k. So we take this signal here, we multiply it with x of k. If I multiply them together, whenever there is a 0 term, they're going to cancel. Whenever there is not a 0 term, we're going to have a value. So in this case, I'm just going to have a value at 0 and 1. So at 0 and 1, I'm going to get a 1 times 2. And then at 0, I'm going to have a 1 times 2. And then at 1, I'm going to have a 2 times 1. So I'm going to have 2 and 2. And then what we do is we add these together. So 2 plus 2 is going to give me a 4. Then what we do is we shift h of negative k by 1. Because we have the index as negative k, shift by 1, h of 1 minus k is going to cause h of negative k to move to the right. And this is going to give me the output when n is equal to 1. We do the same thing. We multiply this with x of k. We're going to get these terms. Then we're going to add all these terms together. Then we're going to shift. We're going to keep shifting h of negative k and multiplying it with x of k. And each time we shift h of negative k, will give us the output at that time shift. So this is, for instance, going to give me the output when n is equal to 1. Here I shifted negative 1 is going to move h of k to the left. This is going to give me the output when n is equal to negative 1. Okay. So we keep doing this process till we have covered any overlap between the two signals. And as I said, we add all these together. We're going to get when n is equal to 0 is going to give me a 4. So therefore, when n is equal to 0, I got a 4. When n is equal to 1, if I added these, it should give me an 8. When n is equal to 2, if I've done it, it would have given me a 2, and so on. When n is equal to negative 1, which is this case here, this is n equal to negative 1, is going to give me this output here. If I multiply, all the terms are cancel. The only term that's going to survive is I'm going to have a 1 here multiplied by the 2 there. Oh, a 1 here multiplied by x of k, which is a 1 here. So therefore, I'm going to get an output that is a 1. If I shift this another time, so if I calculate h of negative 2 minus k, this is going to shift to the left by 1. There's going to be no overlap, and therefore the output is going to be 0. Okay, so this is the evaluating the convolution using the graphical method. Okay. Now let's look at properties of the convolution and of the linear time invariant systems. The first property of the convolution is that it is commutative. So if I take x of n convolved with h of n, it is the same as h of n convolved with x of n. It does not matter the order. So when I've done this graphical method, I could have flipped any of the signals. I could have flipped h of k or x of k. Either one will give me the same results because the convolution is a commutative process. Another property of the convolution is that it is distributive. So therefore, if I have x of n convolved with h1 of n plus h2 of n, that is going to equal x of n convolved with h1 plus x of n convolved with h2 of n. So if I have two systems, I have a signal x of n that goes through two filters, h1 and h2, and the output is added. That output will be the same as if I were to add these two filters together and get h1 plus h2. Another property of the convolution, it is associative. So therefore, if I have x of n convolved with h1 of n convolved with h2 of n, this is the same as x of n convolved with h1 of n convolved with h2 of n. I can do the convolution of h1 and h2 and the result convolve it with x of n, or I can convolve x of n and h1 of n and the result convolved with h2 of n. Either one will give me the same result. Again, x of n convolved with h1 of n convolved with h2 of n will give me y of n. I can convolve h1 and h2, and the result of this convolution is going to give me, if you like, h3. If I convolve xn with h3, will give me the same output. I could have also convolved x of n with h1 of n, and the result convolved with h2 of n. That will also give me the same result. Okay. Another property of linear time invariant system. The linear time invariant system is bounded input, bounded output stable if and only if the summation of h of k is less than infinity. So one way to determine the stability of the bounded input, bounded output system is I'm going to take the absolute value of the h of k terms. If I add them together and they are finite, then that system is stable. And in the class we discussed why I have to take the absolute value, and we said to understand why we need to take the absolute value, if we look at an example h of k where we have h of k values oscillate between 1 and -1, if I were to add them without absolute value, I'm going to get a finite value because the one will cancel -1. But if I have to consider all the possible inputs that can be applied to this system, and I take an input that is also oscillating the same way, 1, -1, then when I convolve these together I'm going to get a situation where the 1 is going to multiply with a 1, and negative 1 is also going to multiply with negative 1, and therefore it's going to be positive. 1 with a 1, negative 1 with negative 1 going to be positive. When I add these together, it's going to be infinity. So therefore, that is why we need the absolute value when we take when we determine the stability of the linear time invariant systems. Okay. Another property of linear time invariant system is that the linear time invariant system is causal if and only if h of n is equal 0 for n less than 0. And what this says is that if I have a linear time invariant system, h of n by definition is equal the output of the system when we applied an impulse at 0. So if the impulse is applied at 0, then if the system is causal, I cannot have an output before 0. So therefore, for the system to be causal, all the output must happen at 0 or after 0. If I have a system where I have an output before 0, and this is the impulse response of the system, I applied the impulse at 0, then this system is not causal. It's not causal because I'm applying the input at 0, but I'm already getting an output before the 0. And this contradicts the definition of causality of the system. Okay. Then we said another, at the beginning we said another form of representing linear time invariant systems is using difference equation. Again, later on we're going to relate h of n with the difference equation and see how we go from one to the other once we introduce or review the Z transform. But for the time being, one way we can use to describe the filter or the discrete time system is using a difference equation. In general, a difference equation, an nth order difference equation, can be expressed as the summation from k equals 0 to n, ak y of n minus k, summation from 0 to m, bk x of n minus k. We have n initial conditions, since we have here n plus 1 terms at the output. So we're going to have an output, one of them is the output, then we're going to have n terms that we need initial conditions for in order to be able to solve them. Now we said we're going to differentiate two types of filters or systems that are going to result from this equation. One of the system, we're going to call it finite impulse response, FIR. The second is infinite impulse response, IIR. What is the difference between the two? If the output, y of n, depends only at the input. So all the terms, y of n is only equal terms, and all these terms are input. X of n minus 1, x of n minus m, etc. Then we call this filter FIR filter. On the other hand, if I have the output y of n that depends on the input and on the output, then we call this an IIR filter. So this is the key difference between the two. The IIR filter is going to have terms of a previous or a future output that is needed to calculate the output at any time. In the FIR filter, the output at any time only depends on the input. IIR, the output depends on the input and on the output, whether it is a previous or a past outputs. Okay. Now, if we look at the FIR filter, I can easily get the impulse response from the FIR filter from the equation of the FIR filter. If I apply a delta to the FIR filter that is written by that equation, then I know at n equal to 0, if I apply a delta as 0, I'm going to get an output that is B0. All these terms are going to be 0, and the only term I'm going to have is b0 multiplied by x of 0. Since I have a delta, and the delta at 0 is 1, I'm going to get b0. So h of 0 equal to b0. If I look at the output at 1, this is going to become x of the delta is going to shift by 1. So I'm going to have an output that is going to be b1. So h of 1, y of 1, which is h of 1, is going to equal b1 multiplied by x of n minus 1. But n is equal to 1. So it's going to equal x of 0. X of 0 is the delta, which is equal to 1. And so on and so forth. H of 2 is going to equal to b2. And therefore, we can find the impulse response of the FIR filter by inspection. Now, the length of the h of n gonna go from 0 to m, from 0 to m, and therefore I'm gonna have m plus 1 finite terms. Now, since h of n have a finite length, then if the summation of all these terms are less than infinity, and if we assume all these coefficients, b0, b1, all the way to bm are finite, then that summation is going to be finite. And therefore, the FIR filter is going to be always stable. Okay. Now, when we look at the FIR filter, the output can depend on the current input, future input, and previous inputs. So I can have y of n equal x of n plus x of n plus x of n minus 1. This FIR filter, this is an FIR filter because there is no dependence on the output. And if I look at y at any time, it depends on a future input and on a previous input. Now let's look at the IR filter. The IR filter, as we will see, it is going to have an infinite impulse response, and that's why we call it IIR, infinite impulse response. And we'll see how we're going to get the impulse response of this filter later. The IIR filter, since it is recursive, since if I calculate the output, it will depend on a previous output. So the output is fed back to calculate the current output. The system is not necessarily stable. The IR filter, we have to check for stability to make sure it is stable. For the IR filter, the output can be a function of future outputs as well as previous outputs and previous and current and future input. H of n in general will be of infinite length. So unlike the FIR filter, where the h of n is finite and it is b0, b1, b2, etc., and we can find it by inspection, h of n has an infinite length. And again, we'll see later how we calculate or how to get the impulse response of the IR filter. Okay, I hope this helps with the material that we covered in this class. If anything is not clear, please feel free to reach out, let me know. We can go over it. Now, lots of this material is considered review, so therefore we did not go into, where is the convolution coming from and how is this translated into this equation. I assume we've seen it in the previous classes, so this is just a refresher on the topic. Thank you, everybody.